So now we're going to be talking about the idea of something called a principal unit vector. And a principal unit vector is actually pretty easy. It's just a vector of magnitude 1 that's orthogonal to the unit tangent vector. All right, so we can see in the diagram below that there's an infinite number of vectors that would be orthogonal to a unit tangent vector. However, the principal unit vector is one of magnitude 1. And that could be useful in trying to find the components. Okay, so you might remember projection and components. So that could be an application of that. But regardless, all we're going to do is we're going to worry about computing these. And so let's say we have a smooth curve on an open interval. N of t is going to be the principal unit vector, and it's defined as the derivative of the unit tangent vector divided by the magnitude of the unit tangent vector. And you can see that this might be a little bit more difficult to work with just because of the second derivative. Two diagrams that I have, one of which is just going through and showing in blue a unit tangent vector which follows the orientation of the curve, and then the principal unit vector which does not follow the orientation of the curve. It could, it most likely won't. All right, so if it doesn't, that's okay. However, if your unit tangent vector doesn't follow the orientation, then unfortunately you're probably doing it incorrectly and you probably need to go back and do some computation again. Same thing in the diagram below. We have a circle of radius 3. The unit tangent vectors are the ones in blue that follow the counterclockwise orientation of the circle, and then we have this normal vector to that curve, and the orientation of the principal vectors are not necessarily going to be the same as the orientation for the curve. So what we're going to do is we're going to take a look at one example first of all of how to find the principal unit vector, and we're going to take a look at an old problem. Okay, so we already looked at this problem earlier in which we found that the curve was smooth and we plotted the curve on a plane, but instead of finding the tangent vector, we're going to find the principal unit vector, and then we're going to graph the principal unit vector, all right, just to make sure it all makes sense. All right, so let's go ahead and plot and also verify that it is indeed smooth. Remember from part A, or from the very first problem we did, it is smooth at t equals 1. All right, we already verified it. And we actually did find the graph. Okay, so remember we had t equals 0. That was the point 0, 0. You might remember we had the point 1, 2. And that's when t equals 1. And that's the point that we're really concerned with. And then just to get a third point, we had the point 4, 4. And the curve looks something like this. We also had an orientation that followed this way. All right. And by the way, this is when t equals 2. All right. And then the other thing that we did was we plotted the unit tangent vector. And correct me if I'm wrong. Well, of course you can't correct me, but we found t at 1 to be approximately 0.7i plus 0.7j. All right, so go back a couple videos and you'll find that. All right, so we probably got a tangent vector that looks something like this. Okay, it's probably not the best I could draw, but it's definitely not the worst I could draw either. So knowing all that, now what we're looking for is we're looking for a vector that's normal to the curve, okay, and also normal orthogonal to this unit tangent vector. So that's going to be our t of t. All right, now that's not going to be easy. Recall r prime of t, not too bad. We're just going to take the derivative of the r, and r was t squared plus 2t. So that's going to be 2ti plus 2j. And the magnitude, and this is where it's going to get a little dicey for us, because we can't just stick 1 in there. If we stick 1 in there, we get a constant, and then when we go to find t prime, it's just going to go to 0. So unfortunately, we can't just plug 1 in there. All right? So r prime magnitude is going to be 2t squared plus 2 squared which is going to be the square root of 4t squared plus 4, or 2 roots of t squared plus 1. All right. And by the way, this is starting part 3. All right. So t of t, which we never found because we didn't need t of t, we just need t of 1, right, is going to be equal to 2ti plus 2j divided by this ugly radical 2t squared plus 1. All right. Another way to write this that's going to be more helpful for us is to rewrite this. Now the 2's are all going to cancel out nicely, and we're going to write this as t times t squared plus 1 to the minus 1/2 I plus t squared plus 1 to the minus 1/2 j. All right, so we're going to hold on to that because now we need n of t. And to find n of t, we need to find the derivative of t of t, and then also the derivative of the magnitude. All right, but we're not going to have to do all that much work, although we are going to have to do some for this. All right, so let's now find t prime at t. All right, and this is going to be the tough part. To find the derivative of this expression, t squared plus 1 to the minus 1/2, we're going to have to use both the product rule and the chain rule of derivatives. All right, so it's not going to turn out too pretty. Derivative of t is 1, and then we just leave the second part of that function alone. So t squared plus 1 to the minus 1/2. Now we're going to leave the t alone. All right, so that's going to be plus t stays as is. We're going to multiply that by negative 1/2 from the exponent. T squared plus 1 to the minus 3/2. And then we have to multiply by the derivative of the interior function, which is a 2t. And that's just our I. All right, so go back through and make sure that you understand the derivative of this. And then we have to take the derivative of the j, which is simply a chain rule. So now I'm finding the derivative of t squared plus 1 to the minus 1/2. And that's going to be minus 1/2 t squared plus 1 to the minus 3/2 times the derivative of the interior function by chain rule, which is going to be our 2t. Okay, and that's going to be j. All right. Let me clean this 3/2 up a little bit, just so I know what it looks like. All right. Now, we can simplify this slightly. All right, so t prime of t is going to be equal to t squared plus 1 to the minus 1/2 minus, so we have a 1/2 and a 2 that are going to cancel. We have a t times a t, so we have a t squared, and then we have this t squared plus 1 to the minus 3/2, and that's our I. And then down here with the j, that's just going to wind up being minus t times t squared minus 1 to the minus, or t squared plus 1 to the minus 3/2 j. All right. Now imagine if you were to find the magnitude of this. Okay, that would be really hellacious to do that. However, remember we're looking for the principal unit vector at t equals 1. So we have a saving grace, is that we can substitute 1 back in for t prime. And that's going to make this a lot easier. Then we can find the magnitude of those coefficients. All right, so we don't have to worry about all that horrific algebra. All right, so if we substitute 1 back in, we get 1 squared plus 1 to the minus 1/2, which is going to be 2 to the minus 1/2. And then over here, 1 squared minus 1 plus 1 to the minus 3/2, so that's going to be minus 2 to the minus 3/2, and that's I. And then over here, 1 times 2 to the minus 3/2, so that's going to be minus 2 to the minus 3/2 j. All right, now I'm going to approximate this. Okay, by the way, if I was to subtract these just to let you know, I did the algebra beforehand. It actually turns out to be 2 to the minus 3 halves I minus 2 to the minus 3 halves j. Right? If you want to see the algebra for how I did that, just shoot me an email, or I can Zoom you and try to figure it out that way. All right. If I approximate this, I think it's 0.35 for both of those. So 2 to the minus 1.5 is 0.35 approximately. So we get 0.35I minus 0.35J. All right, now that's T of 1, however, that's not the magnitude. All right, so we need the magnitude of T prime at 1. Then we can get N. Right? So that's going to be the square root of 0.35 squared plus negative 0.35 squared. All right. So it's a 0.35. And I'm just going to approximate this. All right, so in my calculator, root 0.35 squared plus 0.35 squared, 0.49 approximately. All right, and then finally we can get N. All right, so N at 1 is going to be equal to 0.35 I minus 0.35 J divided by that 0.49. All right, and again, this is not exact, all right, but it's pretty close. So you get 0.35 divided by 0.49. That's 0.714. I have a feeling that if we went through and did all of the calculations, it would probably end up being 0.707, which is root 2 over 2. I might have to use a computer algebra system to verify that. All right, but this just becomes 0.71 I minus 0.71 J. All right, so we're just going to leave it like that because this is a really ugly problem, and that's just the way normal tangent vectors are, or principal unit vectors, excuse me. If we go back up and plot this, okay, which is the last part of the problem, then hopefully this works. Otherwise, we've just wasted 13 minutes. So we have 0.71 and then negative 0.71. So we're going to go to the right, and then we're going to go down. So this is about 0.71, and this is about down 0.71. So we're going to end up with something that looks like this, approximately. All right, and that's good because, as you can see, all right, or hopefully see, right, this ends up being a right angle right here. And if it wasn't a right angle, then again, we just wasted about 13 minutes. All right, so hopefully this makes sense as to how to compute it. Most times somebody would use a computer algebra system, but I did want to show you in gruesome detail how to go through and try to compute one of these principal unit vectors. So I'm going to do one more of these for you in the next video series, and then we'll be done with these tangent vectors and principal unit vectors.